start with the state observer design. In this we will study introduction to state observer, Ackermann's formula for state observer, and we will see one numerical example. Now about the introduction to state observer, why there is need for observer. First of all, let us see the state space block diagram of a system. Let us say x dot equal to ax plus bu, this is your system. Now here say an integrator. Now here is our C matrix and here is output y, here is x dot, now here is b, and input u, and here is matrix A. So here x dot equal to ax plus bu and y equal to cx. Now when we talking about the controller design, so controller design basically in state space is with respect to state. Now here this is a state x here. Now this state has to control. So when we control the state, when it is possible to measure, it may possible that the state x can't be measurable. That means let us say here k x is there, and now we are designing controller through this x. So this is the arrangement of the controller. That means here this u equal to kx u equal to minus kx plus r. This is the controller. But here it is not possible to measure the state x, then how the controller will design? So that is the problem in a state space analysis, because all states need to be measured. So in that case there is need to estimate the states. That means we have to assume, or somehow we should know that states. For example, assuming some problem occurred to us and we are going to doctor, as doctor asks some information and based on this medicine is given, and if you are not cured, then doctor will say you go to higher center. But assume that it is not possible to go higher center. That means whatever the internal thing in our body, let us say urine, blood, everything will be checked. So that can be checked by some assumptions. So sometimes what doctor will take your hand and check the nose like this and see the condition of the patients. So that checking of nose here, it means that doctor is estimating the states. So here also there is need to estimate the state. So then how to estimate the state? So the estimation of the state, it definitely it depends upon the elements of AB, and we have input U. So assume that we have estimated state xc, this is the estimated state, and x is the original state. So xc is an estimated state and x is the original state. What we want that whatever state will estimate, it should be nearer to the original state. That means what we want, the difference between x minus xc, it should be minimum. But how will you know that the difference between x and xc is minimum? Because this x, this cannot be estimated, that is why we are determining xc. Now here the option is that we are knowing the output. So here we are knowing the output of a system, although states we do not know, but we know output. Similarly, we know the output of an estimated state, or we know the output of this estimated state with respect to x c. Let us say output is y, and what is y? Y equals to c into x, and this y e equal to c into x c. That means here c and c is common, and y is with respect to x, and this y e is also with respect to x c. It means that it is better to compare output y as well as the y e. If the error between actual output and the estimated output, if it is minimum, it means that whatever state we have estimated, that is proper, and properly we can design the controller. It means that here the difference between y and y, it must be minimum. Now this is our problem now. So now how will you make all this arrangement? Now in order to understand everything, we need one device which can do the estimation of this, or which can do the correction between y and y. So that is called observer. Now we will draw the diagram for this observer. Say a original plant is like this. This is C, and here is output y, here is x dot, here is x, now here is matrix A, now here is B, now here is U, and now here is the reference R. So this is the block diagram based on the state space model. Now here this state x has to be estimated, but at x we can't know. But what information we have? We have input u, this input is we know, and as well as output y is knowing. That means whatever estimator or a device which estimates the state, it depends upon this input u and output y. Therefore, what we are doing here, we are taking an observer that is called state observer, which estimate the states, and now it depends upon, this is the output, and here is the input which is coming, and from this, so based on the information of input u and output y, now here this is the state x c, and here is our controller k c, and system is completed. So now here we will find that there is a controller k c, which is a controller which is useful for stabilizations. Along with this, there is called observer, that is called state observer, which estimates the states of the system. Now this produces x c, and it depends upon input u and output y. Now what is present inside this state observer? Now we will draw the block diagram of this state observer. Now here is estimated state x c dot, and now here is x c, now here B, input u, here is A matrix, now here is C matrix, and as state x c is the estimated state, therefore here output is, instead of y it is ye, and here ye is the output. And next the output y which is coming from the actual system, you just see here this output is coming here, this output is coming, and it is shown here, this output y is the estimated output, and because of that, because of y and y there is an error, and this error is to be minimized, and therefore what we are doing here, we are adding another controller matrix that is called KE, and here negative. So, here this output, actual output, and y there is a error, and this error has to drive through KE, and what we want, that error which is coming here, it should be minimized, and this minimization is possible because of this KE and this particular state XC. So, once we have got this XC, we have to apply it to the actual system. That means, this XC which we have seen here, this XC is nothing but this XC, and now here it will goes to controller to the reference. That means, this is a closed loop control system, and if your law is satisfied, that means our control law is here Kc to Xc plus u plus r. Earlier our law is minus u, but here because of the modification in the actual system, our control law has been changed to u equal to minus Kc into Xc plus r. Now, this is the block diagram involved the system with state observer. Now, state observer we have drawn independently. Now, what we will do, we combine the both figure, that is this block diagram and this block diagram, and let us see the in what way we will get the final structure. Now, we are drawing the block diagram of a linear feedback system with observer. So, here there are two parts. The first part is related to actual system, and second part is related to observer. Now, first of all, we draw a system. Now, system, the system, this is states called as x dot. So, here integrator x dot, here is x, here is matrix A. Now, here is C, and here is output y. Now, here is your B matrix, and here is of reference R. Now, we will draw the block diagram of an observer. In observer, the states are represented by Xc. So, here Xc dot, now here Xc, this is integrator. Now, here is C matrix, here is Ye. Now, here is the observer gain matrix, or we can say observer type controller Ke. Now, here output Ye. Now, here is, this is a B matrix, and this is U, and here is A matrix A. Now here is Xc. So here this upper portion indicates the observer and the bottom portion indicates the system. Now what is the role of observer? Observer is basically estimates the state by reducing the error between the estimated state and the actual output, that is the output of the system as well as the estimated output. So here estimated output is y. Now here is the actual output. Now here we have to move upper side. Now here negative, it is positive, and because of positive negative, this is y, there is a error E, and it error has to minimize, and as I told you that it is minimized through k, and it is complicated, it is minus k. So now the error has been minimized, but for actual system the state x is not accessible. Now here this state xc we have to move through controller kc coming here, and this input u is same, is coming like this. Now this upper portion is basically an observer, and this portion is our actual system. The input u is common here, this is u, and this xc through kc, this kc is the controller, that is the controller of actual system, and this k is the controller for the observer, because and what is the main purpose of this k is to reduce the error between y and y. So now this is the complete diagram of a linear feedback control system with observer. Now we have seen the block diagram, and we have seen that the error is to be minimized, but how will you prove mathematically that this k matrix, as we have seen this k matrix minimize the error? Therefore, based on this block diagram we have to write down the equations. Output error, that is E, that is equal to y minus y, and the dynamics of the observer, dynamics of the observer is represented by xc dot equal to axc minus ke into E plus b into u. So, if you see this xc dot equal to a into xc minus k into E plus b into u. Now, this axc minus ke, now this error E is represented by y minus y plus b into u. Now here axc minus ke, this y is nothing but c into xc, and this y equal to cx plus b into u, and this can be written as xc dot equal to axc plus b into u plus ke. This negative has been changed to positive, therefore this negative become positive, that means cx minus c into xc. Now let us say this is equation number 1. So we have got xc dot. Now the original state space equation is x dot equal to ax plus bu. Now let us say this is equation number 2. Now we subtract 2 from 1. So 2 minus 1 So, we subtract equation 2 from 1, that is differentiation of this x minus xc equal to this ax and this minus axc. Now, here bu will cancelled and here we will get minus k into c x minus xc, that means here a x minus xc minus k into c x minus xc. Now, here a minus k into c x minus xc, that means equations differentiation of x minus xc, that is equal to a minus kc into x minus xc. So, now we will find that this x minus xc, that means the error between the state. So, that means this x minus xc we can write down as error dot e dot and here a minus k into c into e. If you write equation as x dot equal to ax, so what we are writing down x of t equals to e raised to x of t into x of 0. So, here what we have seen that in order to reach the steady states very quickly, what we want, the eigenvalues of A should be very far away from the imaginary axis. That means it depends upon the eigenvalues of A. Similarly, here also if you write the error equation, let us say in terms of t, e raised to a t equals to e raised to a minus k c into t into e of 0, that means the minimization of error, that is the minimization of error, it depends upon the eigenvalues of a into k c, that means it depends upon a minus k into c. As early the error reduces to 0, it is better for our estimation. So, this is possible when the eigenvalues of a minus k c, it is far away from the imaginary axis, and that means whether it is far away from the imaginary axis or nearer to it, it depends upon this K matrix. Therefore, this is important of a K matrix. K matrix is very important because it governs the error equation. That is why here we will see that we have taken the K matrix, a K from, that is the error between y and y. When it comes to here, the K plays important role. This is because of this reason only. Here we will find that because of this, because eigenvalues depend upon the subtraction of a minus k c, as eigenvalues far away from the imaginary axis, error reduced to 0, and this depend upon this K matrix. The study of, as we have seen, the observer designs. Now we see the various points related to state observer, the device that performs the observation of the state variables based on the information received from the measurement of input and output and their derivatives. Then second point, observer should have the same state equation as the original system. Therefore, design criteria is to minimize the error between xc and x. So, we have already seen that here that we require the error between x and xc should be minimum. So, it is not possible to compare xc of t with x of t, as x of t is not accessible. The best alternative is to compare the output y of t with yt, and state observer can be designed only if the observability condition is satisfied. So, whatever we have discussed, so this has been reported in these 4 points. So, in actual system, it may possible that there are few states, let us say there are say 10 states. Out of these 10 states, 5 are known and 5 are unknown, but what we prefer that, okay, 5 are known, 5 are unknown, it is better to estimate all states. So, if you are estimating all states, even though some are measurable, still we are estimating, that is called full order observer. So, suppose the subsystem observes all state variable of the system, regardless of whether some state variables are available for direct measurement, it is called as full order observer. And similarly, the reduced order observer. Reduced observer means there are some states which are known, which are unknown. So, what we are doing, the states which can be possible to measure, we are measuring it, and which are only unknown, that only estimating, that is called reduced order observer. So, an observer that estimates less than n state variable, where n is the dimension of the state vector, is called reduced order observer. Now, we will see that how to determine the observer matrix K. So, this is possible by Ackermann formula. Earlier we have used the Ackermann formula for obtaining the controller matrix, that is the state feedback control matrix. So, this Ackermann formula is also useful for determining the observer matrix. So, let us see how you get it. Now, consider our original plant as x dot equal to ax plus bu and y equals to cx. This is a plant. So, this is a plant. Without changing the properties, we have seen that this plant can be converted into another form, that is dual form of this one. We can represent by states z dot equal to A transpose z plus C transpose V, and say another variable we have taken n B transpose z. That means what we are doing, we are changing the position of B and C. So, B is earlier here, it has been in the state, it has been transformed into output equation as B transpose. Similarly, the C in the output, it has been transferred to state equation as C transpose V. So, both have the same properties. Now, suppose if you are dealing with this, so what is the control law? The control law in this case, let us say V is the output equal to minus K into Z. So, you can get Z dot equal to A transpose Z minus C transpose K into Z. Now, here equation is A transpose minus C transpose K into Z, Z dot equal like this. So, now we have got equation as Z dot equal to A transpose C transpose K into Z. Now, in order to get the roots of the system, or in order to find out the value of the controller K, we had to assign some eigenvalues. That means, here this equation we have to represent in terms of characteristic equation. So, here this can be written as Si minus A transpose minus C transpose K, that is equal to say S minus M1, S minus M2, say S minus Mn. So, this is M1, M2 up to Mn, that are the, assume that they are the observer poles, that will be like this, and our purpose is to determine the values of this K matrix. Now, if you find that eigenvalues of A transpose minus C transpose K, it is same as. So, if you take the transpose of this particular matrix, so what we will get? You will get A minus, so transpose of this is nothing but K transpose into C. It means that Si minus A transpose minus C transpose K, that is equal to Si minus A minus K transpose into C. And now, our observer state equation is observer state equation is Si minus A minus K into C. Or observer state equation equals to SI minus A minus K into C, and this equation we have got, it means that here we have got this KE equal to K transpose. So, here what we have done, we have taken the system, we have taken the dual of the system, and after taking the dual of the system, what we have got, we have got A minus KT into C, this equation we have got, and our main purpose is to get the value of K, and therefore we have decided the observer poles. Here these are some poles which has to be placed on the left hand side of the experiment to get the value of K, and there afterward what we have done, this A transpose C transpose K can be done in terms of A minus K transpose C from here, and our actual observer equation is SI minus K into C. So, if you compare this one, we got K into K transpose. So, it means that we have to determine the K by actual pole placement technique, and once we get the K, we have to make it K transpose, and we will get the KE matrix. So, as we have seen, we will get the K matrix. Now, in a pole placement techniques, we have seen the different methods for calculating the controller matrix, or we have designed a controller by using the pole placement approach. So, here also we found that the pole placement concept, that is concept of pole placement, has been used in determination of the observer matrix. So, therefore, whatever methods which were studied for pole placement, they are applicable in observer state equation also. That means, we can get the observer observer matrix or observer based controller using the pole placement techniques. So, the formula which we have taken K into K transpose. So, now here we see only one method, and similarly you can use other methods. So, here we see the Ackermann approach. So, according to Ackermann approach, x dot equal to Ax plus Bu, y equal to Cx. So, we have seen last time the controller design in such cases using the Ackermann formula. The Ackermann formula says the controller Kc is equal to 0 0 0 1, and here B A B A raised to n minus 1 B inverse. So, this is the controller for this test space model, and now here we are taking the dual system. Now, for the dual system, here Z dot equal to A transpose Z, C transpose V, n equal to B transpose Z. Now, here if we compare this, and from this we will get K equal to 0 0 0 1. So, the B is changed to C transpose, here we will get C transpose, and A changed to A transpose, we will get C transpose, A transpose C transpose, and here we will get A transpose n minus 1 C transpose inverse into phi of A transpose. This is the controller. Now, our KE is nothing but K transpose. Our KE is nothing but the K transpose, because the actual observer controller is KE. Now, we have to make K transpose. So, when we make the transpose of this one, so all these elements which are written like this, we have to write in the reverse order. So, when you write the elements in the reverse order, the controller KE will get as phi of A, C, CA, CA square up to CA raised to n minus 1, here 0 0 0 1. So, this is the Ackermann formula for getting the observer matrix, or this KE is mainly responsible for reducing the error between the output and the estimated output. So this is the KC formula for getting the controller, pole placement controller, and this is observer controller. So when it is not possible to measure the all states, then in that case there are two types of controller we have to design. One is the controller because of the pole placement, and second controller because of the observer design. So K, C and K are the important things. Now we will solve one example and we will try to determine the observer based controller. Now consider the system as x dot equal to Ax plus Bu, y equal to Cx. Now here A matrix as 0 10 1 0, B equal to 0 1 and C equal to 1 0. And our problem is we have to design full order state observer. So when we are designing the full order state observer, we have to decide where we want to place the observer poles. That means similar to controller poles, we have to place the observer pole. Let us say for this problem the observer poles, let us say m1 equal to minus 10 and m2 equals to minus 10. So when we determine the observer or full order observer, first step is to check the observability of the system. So in this case first step is to check the observability. So check observability. For checking observability we have C transpose, A transpose, C transpose. So here C transpose is 1 0 and A transpose C transpose, if you do the multiplication we will get 0 10. So it is observability matrix. So determinant of observability matrix is 10. So your system is, we can say, observable. Now system is observable, and to get the full order observer we directly use the formula for getting the observer gain matrix. So the Ackermann formula, that is this Ke to phi of A, and here C, Ca inverse to 0 1. Now our desired poles is at S square plus 20S plus 100, because we have pole at m1 minus 10, m2 minus 10, therefore we have got this S square plus 2S plus 100. Now here phi of A will get as A square plus 20A plus 100 into I. So here if you solve it you will get 110 200 20 into 110. Now here m1, let us say this CCA, let us say m1. So this m1 get as 10 0 10, and here if you want to determine this m, that is inverse of m1 will get as 1 0 0.1, and now this controller matrix Ke is nothing but this phi of A which we determined here, then CCA, that is inverse of m1, and this is, that means here inverse of m1 multiplied by this 0 1, and if you do the calculations, so what you will get? You will get the controller matrix Ke as 20 11. So, because of this controller matrix Ke, or we can say because of this full order observer, we are in position to estimate the state of the system. But now there are other things which is also important to be discussed, that now in this problem we have designed the observer, full order observer, but in the system we have to also design the controller. Now here we have placed the pole -10 and -10. Is it the right position to place the pole, or observed pole can be placed very nearer or can be far away? Second case is that about the controller poles, is there any relationship exist between the observer poles and the controller poles, or is there any some conditions that we have to place observer poles far away from the control poles. So, this is also important point. Second thing is that are the observer poles and control poles are dependent on each other. So, this point is to be discussed. So, we will try to discuss this point in the next part. Now, these are some references: Ogata, D. Roy Choudhury, R. T. Stefani. Thank you.